So good evening, everyone. My name is Marawan Zaki. I'm currently an undergraduate student at the University of Toronto's Department of Civil and Mineral Engineering. I'm working with Dr. Konstantin Christopoulos, who's a professor of seismic engineering and seismic resilient design. And our research topic is low-cost seismic base isolation systems for light frame timber houses in North America. So let's start with a little bit of background. According to The Economist, over the past 20 years, 4 out of 5 of the top 5 costliest natural disasters have been earthquakes. Case in point, the 1994 Northridge earthquake, which occurred in California and caused over $48 billion worth of structural and non-structural damage and displaced over 60,000 residents from their homes. Roughly half of these losses were attributed to light frame timber buildings due to their fragile architectural finishes, which can be damaged at story drift ratios as low as 0.17%, even though the code allows us to go much higher to almost 2%. With over 9 million of these homes constructed in seismically active zones in North America, the aggregated economic losses and displaced families due to a seismic event can be quite considerable. The figure on the right over here shows a building which was damaged during a maximum considered earthquake, and this could have been prevented had there been an engineered solution. So how can we protect homes like this and others like it? Well, by introducing a low stiffness isolation layer at the interface of the foundation and the superstructure, we can reduce the force experienced by the building by decoupling the ground and the structure's motions. If you take a look at the graph on the left over here, an average building has a period of 0.2 to 0.6 seconds. With an isolation layer installed, we can have a period of 1.5 to 4 seconds, greatly reducing the accelerations, and by F equals ma, greatly reducing the forces. However, we do pay for that with an increased displacement. But again, we can control it with an increased damping system, as well as providing a moat which allows the house to move without being damaged. We must also balance this by the cost of designing, manufacturing, installing, and maintaining these devices, as they can be quite expensive and hard to massively implement. So on the right over here are the 4 devices that we're looking to test and study. The device on the top left and the bottom left are rolling and sliding isolators respectively, and they work very similarly. The top steel plates shown here and here will be attached to the superstructure, while the bottom steel plates shown here and here will be attached to the foundations. During an earthquake, they'll be allowed to move independent of one another based on these articulated PTFE sliders or rollers. And the shear transfer and deformation characteristics of these isolators will be primarily controlled by the coefficient of friction of the steel surfaces, mu, which ranges between 0.03 and 0.2. We can also further increase the effectiveness of these isolators by introducing curvature to the bottom of the plate, allowing the devices to recenter themselves after an earthquake, which I'll describe later why it's so important. On the top right over here, we have an elastomeric bearing isolator, which consists of alternating layers of steel shim plates and hard rubber, which are bonded and vulcanized under high temperature and pressure. These bearings exhibit a very large vertical stiffness due to the steel plates, but they have a very low lateral stiffness, which is a function of the ductility of the rubber. During an earthquake, the rubber will lengthen and it will dissipate the energy of the earthquake as heat energy. And on the bottom right over here, we have a rocking isolation system, which utilizes geometric ductility to counteract the earthquake, essentially creating what we call a controlled soft story mechanism. During an earthquake, the columns, which are attached to the foundation, are allowed to rock about the base connection due to yielding screws, which act to dissipate the energy of the earthquake due to the hysteresis. This rocking is mainly controlled by the geometric properties of the column, including its height, width, and mass, and so can be really accurately engineered to suit each building. So this project is still in the beginning. I just started it in May. However, we've identified 6 key steps for the success of this project. First is the statistical selection of test building properties to best match real-world applications. Based on a literature review, we decided to go with the Curie Caltech index buildings designs that were done by Dr. Philly Tratt of Buffalo University. We chose 4 buildings, the small bungalow, all the way up to the multi-story apartment complex. Second will be the statistical selection of relevant ground and wind motions for service and ultimate limit states. This will be done in accordance to ASCE 7-10, as well as the Peer Ground Motion Database. Third, we'll be doing numerical modeling of the structures and the isolation system using a reliable finite element model or discrete element model software such as OpenSeas and Sapwood. We will then go about optimizing each isolation system by altering the device's parameters and configurations, including materials, dimensions, and integration with the building. After we've optimized each system individually, we'll choose the most optimal isolation system using a weighted decision matrix focusing on cost and performance. And finally, we'll be doing physical testing of the specimen in the laboratory to validate our numerical simulation. And if it's successful, we'll put forth a design methodology. In terms of the validation metrics that we're going to be looking at in order to determine the efficacy of our systems, we will be looking at peak story and residual story drifts, as drifts larger than 0.17% can indicate damage to the structure, as I mentioned before, and residual story deformations can compound damage from future earthquakes. We'll also be using accelerometers to measure each floor's acceleration, as large accelerations carry large inertial forces, which can cause damage to the structure. And finally, we'll be looking at the visually observed level of damage during testing, due to the fact that large observed damage can cause occupants to perceive the structure as unsafe and can indicate non-visual damage. And we'll be balancing this all with the isolation system cost, as a low-cost system can be more widely implemented. So overall, this project is in the very beginning stages. However, I do believe if it's successful, we can prevent potentially billions of dollars worth of damage and displacement due to earthquakes. And for mass implementation, we want to have a low-cost, reliable, and easy-to-install isolation system, as well as a design methodology to accompany it. So thank you all for listening to my research, and I welcome all your questions.
Thank you for your presentation. Judges, again, feel free to ask questions.
Hey, Marawan, thank you for your question, for your presentation. So I just have a quick question on, do you think there will be any implications of your project on revising building codes or the way construction is done?
I certainly think that there will be a bit of implication about that. Currently, what the building code specifies is what we call capacity design, which is essentially to ensure that there is no, it's to minimize the damage to the buildings, but more importantly, to ensure that there's no loss of life. However, what designers in the seismic field are now looking at is performance-based design, which is not, or resilient-based design, which is not only to minimize loss of life, but also minimize damage to the structure. So for example, going back up here, we can see that the structure is still standing, the occupants would be safe. However, it's unusable and would have to be, teared down and would cost the home occupants millions of dollars. So I certainly think that something like this project would move the needle towards performance-based design and hopefully focus more on the economic side as well.
Thank you, Marwan.
Hey, Marawan, it's Professor Evans. Wonderful presentation. Interesting to see the results. I like that you're going to be doing a combination of computational and then some physical testing. So I have two questions for you. One, I didn't quite understand what you meant by statistical selection of conditions for wind or for ground displacement. Yeah. And then there's a second question, which is about the scaling. When you do physical testing, what size, what scale will you do this at, and how do you think about scaling it up to the size of full-size buildings?
Yeah. So to talk a bit about the statistical selection of the ground and wind motions for service and ultimate limit states. So currently, the ASCE or the Canadian Building Code, they do give us a way to calculate what we call response spectrum, which is this black, really clean line that you see over here. However, it's kind of a blunt instrument. It's based on approximations of the soil characteristics, the site characteristics, and so on and so forth, and the building characteristics. So what we can do to make this a little bit more accurate is to look at other earthquakes that had occurred in the past and in different regions, and try to compare them and really hone in on the most relevant earthquakes. So to do that, we go through a database and we kind of filter through multiple layers in order to get the most accurate and most representative earthquakes. And as for the scaling of the tests, so we are actually following in the footsteps of some other tests that have been conducted out of Stanford University and Buffalo University. And for those tests, they actually were able to do full-scale testing. So they had buildings that were perfectly modeling their conditions. At the University of Toronto, I don't believe that we have the space in order to accommodate that. However, half-scale testing would be doable, or partnering with another university, or even doing hybrid simulation by physically testing the isolators, but numerically testing the building's results. So it would be a hybrid test of numerical and physical at the same time.
Wonderful, thank you.
Okay.